Hello all, this is Can Dede. This is our first lecture in the course called Dynamics. We will have a brief introduction to the concepts of dynamics. Dynamic studies belong in a greater subset of engineering studies and in the large set of mechanics. And mechanics deals with the motion of particles, bodies, and body systems, or systems that are composed of bodies. And these particles can be in the form of rigid bodies or some flexible bodies or even fluidic systems. If you're dealing with the fluidic systems, then the type of investigation that you're doing falls under the fluid mechanics work. In fact, this work could consider the statics and also dynamics. So there's fluid dynamics and hydrostatics type of studies available, and you will actually have these courses on fluid mechanics for 2 semesters in this engineering school. This semester you're also taking another course on strength, and in this course of strength, in terms of mechanics, you're in the domain of deformable bodies, and in strength you try to understand the mechanics of these deformable bodies. These bodies actually are flexible, and under the influence of forces, these flexible bodies have compliant displacements and they deform. In this course, we will be working in the domain of rigid body mechanics. So this is our first ever assumption in this course. In this course, we are dealing with rigid bodies and rigid body systems. But prior to that, we would understand the mechanics of particles, system of particles, and finally we're going to define rigid body, and we will work on the mechanics of rigid body. In fact, in the prior semester, you have already worked in the area of statics. In statics course, what you have done is to relate forces acting on a body to each other, right? And then the assumption that you had in that course is that this body or system is not in motion. It's stationary. That's why it's called static, right? It's in a static condition, and then you're investigating the relationship of forces. Now, in this current course, we are dealing with dynamics, and in dynamics there is motion. So the first thing that we're going to study is motion. We're going to relate motion of the particles and system of particles, and then rigid body and rigid body systems by using the study of kinematics, and the generally accepted term for this study is kinematics, and we are disregarding any forces acting on the body in the study of kinematics. We are just considering motion relationships. Now, in the second part of this course, we will talk about kinetics, and we will, in this case, relate forces acting on the bodies to the motion of these bodies. In order to relate the motion and force, first obviously we need to understand the motion. That's why in the first part we do kinematics. We're going to start with the particle kinematics, then move on to the kinetics of these particles as we understand the motion of particles. Then we will visit a system of particles, and then talk about its kinematics and kinetics. And finally, a final assumption will be done for rigid bodies. And in this final assumption, we're going to consider these bodies as rigid, although there is nothing rigid in the world or in the universe. Everything has somewhat flexibility and can deform under forces. However, we have this assumption that a rigid body does not deform, or it deforms but it's negligible, so that we call it a rigid body. So this is an assumption. And before moving any further, let's take a look at the basic concepts and the definitions that we're going to talk about in this course. We should have a common understanding of these basic concepts. Space is the measurements are made relative to axis frames. We can use different type of space for understanding motion of particles. We can use three-dimensional space, we can use a two-dimensional space, even we can use a rectilinear case. For example, think about the sliding door. Sliding door itself is a three-dimensional object. However, the type of motion it does is it slides on the rail, and it only does a sliding motion. It's rectilinear motion in that case. Rectilinear means that it's a linear motion in one axis, so it doesn't move anywhere else. However, if you have ever slided a door, you can actually imagine that it can move up and down a little bit, so the constraint that you have is not that fixed, so that it doesn't really move on a straight line, but it might have a motion something like that. It can move up and down, but it's very limited. Nevertheless, it can move up and down because there is a clearance. There is this. You need to have clearance between this rail and the door itself. Otherwise, it's not going to move. It's just going to stick. You need these type of clearances in these type of joint structures. This is a new word that you will see commonly in the next year's course on theory machines. Joint. In Turkish, it's called mafsal. Now, with respect to this clearance in the joint, obviously there is this motion of up and down. So if you consider this as the x-axis, this one as the y-axis, there's a motion in the y-axis, but then you make this assumption. Okay, you say, well, this motion is quite small, so let's assume that it does a rectilinear motion. So with respect to these assumptions, we can define the motion of particles depending on the nature of their motion. We can say they are moving in a linear path, rectilinear motion, or it is moving in a plane. So there is our particle and it has this motion path on the plane. It moves towards this direction, x and y. Or we have this particle moving in three-dimensional world, x, y, z. And then there's our particle. It has this type of a motion in three-dimensional world. However, we define these motions with respect to these frames, as you can tell. We can define the motion of this particle with respect to xy frame or xyz frame. And if this frame is stationary, that means it's fixed to the earth. So this is the way to resemble that this is fixed to the earth. It's not moving relative to the earth. Then the type of measurement that you do about the motion of this particle is an absolute measurement. If it is not fixed to the earth, so you have this train, and then the train moves on this rail, and then you're this guy also walking, and you're observing the motion of the train. So the observation that you do is based on this fixed frame onto your head. However, your head is not in a fixed location with respect to Earth. You're moving as this train is moving as well. So the type of measurement that you do is a relative measurement. However, the absolute velocity of a particle or a body would be measured with respect to this fixed frame, and the fixed frames are usually called primary inertial frames or inertial frames in short. And then we have this assumption that they are fixed in space or fixed to the earth in our case, as we are not doing anything in the space. Mostly in this course we're not going to deal with space problems, but if it is the case, then probably we would be using a frame that is fixed to the distant fixed stars. As they are more distant, their appearance to us will be more fixed, and then in navigation, in the first years of navigation, people used to use this type of distant fixed star frames to find out where they are around the Earth, actually, and how they are moving relative to these distant fixed stars. Anyways, so a measurement done with respect to a primary inertial frame or fixed frame would be called an absolute measurement. Time is the measure of succession of events. So the events happen successively. There is a valid discussion, obviously, about the absolute time or relative time. However, we're going to use the absolute time. So the time that at somebody in the train, for somebody in the train, and the time for this guy observing the train is the same time. So we are using the concept of absolute time in this course. Mass is a measure of inertia to change the motion, or you can call it the resistance. You actually resist. So if you consider this famous equation, which we'll see in the next video, as F equals ma, Newton's law, this force acting on this particle with a mass m results in the acceleration. But if this mass is large, then the resultant acceleration, which means the resultant motion, will be a very small motion. Therefore, your resistance to the motion increases as this mass increases. Force is the action of one body to another, and this could happen via direct contact or via remote action. By direct contact, we have these mechanisms to do such things. For example, the engine of a car, there is our piston moving up and down in the cylinder, okay, and then this is connected to the crankshaft, and then as a result of this, the crankshaft rotates, and the force as a result of the combustion in this cylinder results in the rotation of this crankshaft, and you're actually relating this force to a torque around this shaft, and the shaft rotates as a result of this relation. And this happens through direct contact. You have these joints, revolute joints, rotational, that means rotational joints. There is the sliding joint of the prismatic or the prismatic joint of the piston cylinder, and as a result of that, the crankshaft here rotates about this axis. Or this could happen via remote action. For example, gravitational action. There's nothing actually in direct contact to us while we are feeling this gravitational force. This is a pulling force, and we're going to explain the universal law of gravitation of Newton in the next video. It could happen due to electrical fields or magnetic forces. These are the forces that we would feel by remote action without any direct contact to our particle. Now, having said that, we have talked about particles a lot. We said that in this course we're going to first consider particles, then system of particles, then the rigid bodies. Particle means that it's a body of negligible dimensions, so it's basically dimensionless, if you would call it like that. And this is again an assumption, so there's nothing without any dimensions, obviously, but the assumption is that it has a negligible dimension. So you can think of this as a point in space, just a point, and it could have a mass, but then because it doesn't have any dimension, it's not a circular thing or spherical thing, it will not have this moment of inertia or anything like that. So as a result of that, you're not going to consider the rotation of a dot. It's just going to move in 3 dimensions. The type of motion it could have would be a translation in x, y, and z axes. So it could have this path. It could have a path like that in a 3-dimensional world. However, it's not going to rotate. So that will ease our calculations, first of all, to understand the nature of the problems. And in fact, we can use this assumption in many cases, even in the sliding door example, because yes, the sliding door maybe rotates a little bit around its rail, but you can assume that that really is a small motion. So you can even consider that large door that slides on this rail. So you have this door sliding on this rail. Let's draw a nice door here. Okay. And then there's this handle, and it slides back and forth. But even that, you can consider this as a particle, and you can call this just a mass of m, since it doesn't rotate. Okay, and then this would be a valid assumption. There's a force acting on it, F, and as a result of that force, it's going to have an acceleration that is equal to F over m. So we can solve a lot of problems by using this particle assumption. Lastly, I already talked about it a little bit, but rigid body. What does rigid body means? Well, in fact, you can think of these bodies as a combination of particles. In a sense, you could have a discrete combination of these particles, and then you can say a body is composed of many particles. However, the rigid body assumption is that these particles do not have, the particles that compose this rigid body do not have motion relative to each other. That means their shape, the shape of this body, does not change in the influence of any forces. So the deformation of this body doesn't really happen. If a body does not deform, or it deforms but its deformation is negligible compared to its overall dimension, then we call this body a rigid body. But like I said, this is just an assumption. In the real world or in the universe, we don't have any rigid bodies. Every body, even the hardest metals, have some type of flexibility or some magnitude of flexibility, and this is just an assumption to ease our calculations in the study of dynamics, rigid body dynamics. And then from that point on, you can move on to some advanced studies where you're going to consider also the flexibility of these bodies.